Today, I would like to share some working experience about how we speed up our SQL workload, especially in the cloud. I'm an engineer from Alluxio. I also have some Alluxio stickers put on that table. I'm also actually an open source engineer. I'm working for Presto DB community. I'm also a contributor to the Trino. I'm also working with the Iceberg, Hoodie, Parquet, this kind of community to improve their efficiency and also their adoption to the computer engines. Okay, we can start my presentation. Today, I will introduce some details about Presto and Iceberg. Actually, my talk is not focused on Presto or Iceberg. I just use Presto and Iceberg as an example. I'm talking about how we can improve the efficiency of the I/Os of this kind of a computer engine. Because if we are talking about the Spark SQL, if we are talking about Impala, they're pretty the same. They are follow very similar ideas. And then I will also talk something about the SQL execution. Because before we talk about I/O, we should know how the computer engine to execute the SQL. And then the third part is I think the most juicy part is how to accelerate this kind of SQL, especially in Presto. Again, I'm just using Presto as an example. We can apply the very similar idea to Impala. I think the same thing. Okay. Here's a short history of Presto. I think it starts from earlier than 2013. Initially, it's developed by some engineers from Facebook. And then there's a lot of community work. I think the major milestone is in the 2019, the community split to Presto and Trino. Yeah, there's a lot of story there, but I don't want to share today. But now I'm focused on Presto DB, but sometimes I also contribute to Trino. They still share a lot of very, very similar ideas, but the code base they diverge. There's a lot of things that make you something really, really different. If you want to contribute to Presto, someone want to cherry pick your contribution to the other side, there should be a lot of efforts now. But design ideas is very, very similar. Okay, the overview of Presto. Just as I mentioned, it's just a SQL engine. I think originally it's designed for the Hive data warehouse, but now we are more saying we are SQL on everything. Because a lot of people actually, they query their Hive data warehouse. It's still the majority of their use case. But they also use Presto to query their Hoodie, Iceberg, something like a data lake. And also in the Presto, they have a Kafka connector, so you can query the data on Kafka directly. But the scalability of this connector has some issues. So if you really want to query some large scale, large volume Kafka topic, there might be some issue. It's quite slow, and sometimes it's overload Kafka. We also have some Druid Peanut connector, also MySQL connector, which means we can connect the real-time database or storage into your offline or batching data process job, which means you can join your Hive table with a MySQL table. And also you can join your Hive table even with a Google spreadsheet. A lot of data scientists, they really would like to do that. They create a very small table in MySQL or their Google spreadsheet, and something like a translator, they can mapping the large table in Hive with their small tables. They can get a better understanding with their data. I think if we're talking about something 8 or 10 years ago, the Presto is just for the ad-hoc queries, which means the data scientists, they will make their query manually, right? They send the query to Presto and just waiting there for their results. So most of the Presto query should be designed can be finished in from 1 minute to 10 minutes, something like that. But nowadays, we are seeing more and more companies that are using Presto to serve their dashboard, which means the query might be much small and could be finished in 10 seconds. Even though I heard some companies they are using Presto to serve the sub-second, which means the query can be finished in 1 second or maybe 2 seconds, something like that. And the number of queries has been increased significantly. When I work for Twitter, I think for Twitter in the early stage, we only serve 10,000 queries per day. But after we adopt the dashboarding and the BI tools and A/B testing queries, I think the traffic or the workload increased 100 times, 1,000 times bigger than before, just because their dashboard, for each dashboard, they may have 100 charts, which means they have 100 queries to run, and they might schedule their dashboard to be run in every 10 minutes or 30 minutes, something like that. If they have 1,000 dashboard, maybe it's just 1 million queries per day, something like that. Okay, and the other use case is some company has been started to use the Presto for their ETL job. But the thing is, something like Presto, like Impala, they're not really designed for the ETL job, which means they're not really for tolerance. If something happened in the middle, it's not something like Spark or like the Hadoop, the MapReduce. They can retry in some checkpoint or just retry the reducer or something. If something wrong in the middle of your Presto query, you have to restart your query from the very, very beginning. But it's not, for now, it's not a big issue because because for the ETL here, mostly it's just a lightweight ETL. Most of our customers, they're just using something like Airflow to trigger the query. So they can retry the entire query on their Airflow. So there's not a big issue. But there's still some issue. I will talk later. Yeah. Okay. Here's the architecture of the Presto. Yeah, just because if we're talking something about the SQL planning, we're talking about some I/O, firstly, we have to know how it works. Actually, the design is quite simple. It's not something really scalable, just because the Presto has something like a coordinator. For each Presto cluster, it can be very huge. It can have some maybe 500 workers or something, but they only have one coordinator. And you can see all the queries from client, it will go to the coordinator. And also all the results, query results, the data results can maybe generated from the worker. It also goes through the coordinator. And in this case, the coordinator will be the single point failure, and also it will be the bottleneck. But that's just how they design. So you cannot make a super huge Presto cluster. Maybe for each Presto cluster, I think the limitation I tried is just something like 500. More than that, we can see the coordinator might become superside. Yeah. And the thing is how the Presto is working is, the Presto is not something like a real database. We call it storage independent, which means we don't have any data. We don't need any data ingestion. For every query, we load the data from the external storage. Which means every time it will try to load the data. If the external storage is on premise, maybe some HDFS, it can be fast or not. But if it's on cloud, if you're using S3, you may suffering from some really slow network connections, throttling, everything. And also, here's for the data. But for the metadata part, the same thing. Presto won't host or store any metadata. So every time you send a query, something like maybe you query some tables, all the metadata about this table will store in some external metadata store. For the most common use case is the Hive data warehouse. So for each Hive table, they will create some, just talking about the common use case, they may deploy a MySQL. So they put each table as one entry in the MySQL database. But sometimes for each table, you may have more partitions because you cannot put all your Parquet file, data files in one single directory. You may partition your table, which means you also need to maintain the partition information in the metadata store for some really huge tables. Because for some tables, I have seen a lot of customers, they are partitioning their table by the hours. So which means for each hour, they'll create a new partition. So if you are talking about for 10 years data warehouse, they may have 10 years the hours. I don't know how many hours for 10 years, but it's quite a lot of partitions. So that might become a bottleneck because when some guy want to query this table, the Presto coordinator will try to load this kind of partitions from the meta store. For higher tables, this kind of thing will be loaded from MySQL. And in the MySQL database, they may have multiple tables, something like the one table for the table information, the other is the table for the partitions. So in this case, the partitions, the coordinator will trying to load the partitions by the table name from the coordinator. Okay, here's the Iceberg Overview. As I mentioned in this slide, the coordinator will try to load the metadata from some externally. But if we're talking about the Iceberg, because the Iceberg will maintain their metadata by themselves. So they store the metadata in a couple of data files. In their concept, it's called manifest. And also in the Hive tables, because they store data in the MySQL, just as I mentioned, if something got new, it will overwrite your previous metadata. So in here, in the Iceberg, because they are storing the metadata in some data files, in just some JSON files or Avro files. So they can maintain multiple versions of the metadata. They call snapshot. So here you can see the S0 and the other is S1. Here the S0 is the snapshot 0 and the S1 is the snapshot 1. They can maintain different versions of the metadata, which means they have different versions of your manifest. Which means for the data files, they may share, and for the snapshot 0, you can see on the left side of this diagram, you can see the snapshot 0. It only contains the first two sets of the data files. See, we have 3 sets of the data files on the left, right? So for the snapshot 0, it only contains the first 2 sets. And for the snapshot 1, which means maybe some other users, they append some new data set, to the snapshot 1. So they maintain some new files. So by doing so, they can do some time traveling, as I mentioned here. So if you want to try to query some data yesterday, you can just query from maybe the earliest snapshot and just run your query on the subset of the data files. And also you can do the rollback. And the same thing, because you have a different manifest, you can also do some schema evolution. Because for the Hive tables, they are sharing the same metadata, right? It's the same. Here, the schema is something like something like a column definition or something. So if you add some new columns, it's okay. But if you rename some columns or you change the columns, the type of some columns, it will break your old data. So that may become a disaster sometimes. But if you're using Iceberg, it will become much better because you have a snapshot, you have multiple manifest, and they maintain their mapping shape between the columns. If you add some new columns, you rename the columns. It can provide somehow some backward capability for your Iceberg table. Here is the Presto plus Iceberg deployment. For the Iceberg itself, it's not something like a service. It's just a table format, and it's more like a library. So you can just embed the Iceberg library into a Presto. And with our Iceberg connector, I think we contribute the Iceberg connector, I think 2 or 3 years ago. So now that the Presto support Iceberg, you don't need to deploy anything else, just the Presto. And then you can make the color is not so good, but anyway. So it's still the same thing. As I mentioned, you cannot make a single Presto cluster too big, but you can have a federation of your Presto cluster. You can have more than one Presto cluster behind a proxy. So the proxy can route your query into some specific cluster. And the cluster can, as I said, the yellow ones, the connector plugin. Here we're talking about the Iceberg connector. We're talking about the Hoodie connector. It's the same thing. There's some different connectors. It will link to the data, to your storage. So the data can store in your HDFS. As I mentioned, it can be Druid, can be S3, can be everything. Okay, then let's talk a little bit about the SQL execution. So for a single SQL, no matter it's a Hive SQL or Iceberg SQL or Hoodie SQL, because we can have something like a syntax tree, we can pass in it, we can generate the plan. On the left side, actually, it's the logic plan based on the syntax tree. I just use some simple queries, something like select something from table and where some conditions. There's no join. So for this simple queries, for the logic plan, it's just something like the first step is we scan the table, and then we apply the filter, and then we populate the output. But we can do further optimization. So we are talking it as a physical plan. So in the physical plan, we can scratch some of the filter into the scan, because during the scan, because as I mentioned, the Presto, there's no data injection. It will load the data from the external storage. So when you load the data from the storage, which means if we can reduce the number we read, it will speed up your query. Am I right? So we can just scratch, or we call push down some of the filter into a table scan. I can talk why it works, just because the data format of your data file. So if we're talking about something like the CSV files, like the JSON files, if we push down some criteria or some filters, it won't work, because it always reads through from the very beginning to the end. It will read the entire file. But if we're talking about the Parquet files, because it's column-based data files, they have some, we call it structured data. So we can talk a little bit about the Parquet format. So in the Parquet format, there's a footer. There's a footer at the end of the file. And in the footer, they have some stats, something like the minimum value, the maximum value, into the Parquet reader. It works. For example, if we want to query something like by the age maybe greater than 20, by checking the stats, if we found for the entire files, the maximum value of the age is just 18 years old, so we can skip the entire files. And also, if we're talking about the columns, we can see the Parquet file are split to some row groups, and for each row groups, the data will cluster by the columns. So which means for the data for each column will store together. So if we want to select something, we will select A, we want to select B, or we want to check the A greater than 5 or something. We don't need to touch other columns. So which means we can skip other columns. So by reading the footer, then we know the structure of the entire Parquet file. So the Presto will always read the Parquet file from the footer. Okay, so after it passing the footer, then the Presto knows the entire structure of this Parquet file, and then it can skip some sections. So that's why in my previous slide, I'm talking about we can apply the, or we can say the push down the filter into the table scan, and by checking the format of the Parquet files, if we're pushing down the filters into the table scan, we can skip a lot of files in the Parquet readers. We're talking about that because in my next sections, we're talking about the caching part. So which means because as I mentioned, the Presto will load data from external storage. So if we want to cache some data on Presto side, we don't have to cache the entire files because we always writing SQL with some criteria, with some filter. So we will skip a lot of things. With some high selectivity queries, we are seeing for most data files, they just read something like 8% or 10% data just in one file. Okay, here's some concrete example. It's not a formal benchmark. I just make up the data. So we can see by enable the predicate push down, let's just focus on the input rows. So the input rows, without the push down, the input row will 2 million. But after the push down, the input row is just one rows. And the input data, previously, it should be more than 200K, and after the push down, it's only 559 bytes. Yeah, we can, but this is make up example. In the real case, it cannot be so much. But I just want to talk about for my queries, we don't need to read the entire file. But here's the thing. If we are talking about the storage on cloud, I'm just using S3 as an example. I'm not saying that S3 is bad or not. I'm just talking about the storage on cloud, especially for the object storage. Mostly it's designed for getting the entire things. So for this one, if you're checking the implementation of the S3 client, it will try to open HTTP stream. It will read the entire object. For sure, you can specify a range, but again, as I mentioned, it's optimized for the sequential read, but actually the Presto is read data from the very end. It will read the data for the footer first. Actually, it will read the last for, maybe not for 10 or whatever, the last couple of digits, bytes from the Parquet file, and try to locate the footer, and then it will seek back. It always seek back, and then it will reach some row group, and after it reaches row group, it will seek forward. So it will jump back and forth to find the right position to read. But for this kind of syntax, for this request syntax, it's not fully optimized or designed for this kind of position read. So that's caused the issue. So if we want to speed up I/O, probably we need to prefetch or cache something. But in this case, it won't work because we always jump back. And sometimes we also jump forward. So it will cause a lot of trouble. Okay. So here is our local cache solution. It's not my work. I think this work is start from 3 or 4 years ago. It's the collaboration between the Facebook and Alluxio. So we are start using something we call local cache on Presto side, which means during the scheduling, because as I mentioned, the Presto will load the metadata and trying to load the data and trying to seek the data file. When we locate the data files, the Presto will schedule the split. We call it split, but actually just the scan task to each data file to the workers. Now we are using something called soft affinity. So we are doing some hashing based on the file name, which means after that, for the same files, it will always go to the same worker. But it's affinity, it's hard affinity, right? But why we call it soft affinity, just the Presto will check the workload of that worker. If that worker is too busy, we will schedule this place to the second worker. If the second worker is still busy, we will reschedule to the third worker, something like that. So it's more like the soft affinity. So it's a balance between the workload and the cache hit rate. Yes, and for each worker, because the worker may always receive the same amount of the same set of the data files, so we can cache it. And we cache the read, the data we read from the underlayer storage like S3, like HDFS, to the local SSD. That's why this project is so popular, just because for each Presto clusters, they will have some SSDs. They always have some SSD, but they don't use it because the Presto, we rarely store the intermediate result to the SSD. So it's just we are wasting the results somehow. So now we can take advantage of the local SSDs to store the data we cached. And as I mentioned, we don't need to cache the entire data files. So here's the storage structure. The storage structure of the local cache. So for each files, we will do the hashing and we will make it as a bucket to some local folders and the block IDs because we store the data based on the blocks. But it can be the hashing value of the file names. It's the same thing. And for each originally, we keep everything. So for each block ID, just a single file. But now we are using something that we call the pages cache, which means for the entire files, we want to keep the entire ones. We based on the offset you read, we will generate some page. So if you just read the footer, let's use an example like if the page size is 1 megabyte, if you read 64 megabytes Parquet files, but if you just read the footer, we only cache the last page, so which means for the page numbers, there's only one page there, it's the 64. So we want to cache the entire files. And also for the write case, we can have something like a temporary folders to store the data we write, and then it can be committed to the formal ones. And yes, so by doing so, we can cache the data in the Presto workers, and when the Presto workers got something in the cache, it's just read from the local SSD. So as I mentioned, I think the footer may be the most hot data. So if we just cache the footers, just use this example, so all the footer will read from your local SSDs. It won't for this kind of file, it won't touch the under storage. And because it's a local SSD, so it can be random accessed. It's not something like S3. We have to send a HTTP request. We need to build out a stream. So it's not necessary. We can just read through the local SSD. But we got some issue, like every cache we may have some data consistency issues because some of the data files or partitions maybe got updated. Because as I mentioned, especially when we start using Iceberg, using Hoodie, they have snapshots. They are more like you using their Iceberg tables, more like OLTP because they are transactional. So they keep insert rows to the existing tables. In this case, the data files got updated. Even in the Hive tables, they're also true. But this rarely happens, I have to say. But sometimes if some data engineer found something wrong, they might want to backfill your hive tables. So if something got updated, as I mentioned, we just use the file name or the path of the file as the key, the Presto won't know this file got updated. So now we are using the partition and the file ID. It's here the path, and we are adding some last modified time into the cache key, because the coordinator will list your data files, will get the list data from the under file storage, and it will have the status for each file. In this status, we can get the last modified time of each files. We are pushing down this kind of information from the coordinator to the workers. And in the worker, we combine the path with this last modified time. So it's a combined key, which means the previous cache key is just some path. It's a MD5 or some hash functions on the path. But the new caching key would be the HDFS path plus a last modified time. And so if some data got updated, the Presto coordinator will try to list this kind of file first, and we will get a new last modified time. And because the file paths are still the same, right? But the modified time are different, so we will get a new cache key. So with the new caching key, it won't hit the old data. It won't hit the store data. So we just read from always we read from something new. If it's not there, it will reload from the under file storage like S3, like HDFS. But the thing is, if some table keep updating, we will always generate the new keys, right? For the old ones, they are still in the cache. They're still there. They cannot be got evicted, right? So, but we have some eviction strategy. So finally, maybe 1 or 2 days later, the data will be got evicted. But somehow, because the caching is more expensive, that the caching space is limited. So probably we want to this kind of old invalid data to get evaded earlier. There's some work contributed by Tencent and TikTok, but I didn't merge it to the master just because there's some trade-off back and forth. They're not using the last modified time in the key. They are every time they based on the last modified time, they will try to check. They store the last modified time in the cache entry in the page, the file name of each page. So if by checking if they found the data is stored, it will try to evict the data first rather than create a new key. But again, in the Presto master, we are still using this approach, rather than do the eviction on demand. The other thing is because we are trying to calculate the path. We are trying to calculate the path by the file name, but what if we are adding more nodes to the Presto clusters, or maybe some nodes that's offline or lost in the middle? It means we compute the file name into a hashing, and we mod the hash by the number of nodes, but we have more nodes or less nodes. It will hit to some other nodes, which may cause a significant cache hit rate job somehow. I just use this one as an example. So if the key is 4, it will always go to the worker 1, right? But what if the worker 2 got offline? Then we have only 2 nodes. If we still following the same algorithm, it will go to the node 0. But unfortunately, the worker 0 does not contain this kind of data. So you will see the cache hit miss. And if you have maybe 100 worker or something. So if the hash shifted, you may see the cache hit rate is pretty sad. It will drop to maybe 5% or something, maybe even lower. So we involved consistent hashing rings to solve this problem. I think this one is already merged into the master. So we build a hash ring based on all the nodes. So if some of the nodes temporarily got offline, it's still a hole or something there, and it will just go to the next ones. For the other node, there's no impact, and for the other data files, because it will still go to the old workers, so that your cache data is still there. By doing so, we are still seeing a cache hit rate drop if you are offline 10% of workers or add 10% of new workers, but the impact will be limited. Just maybe we can see maybe 10% of cache hit rate drop. And also, I think that the most challenge we are facing now is just because the efficient cache space. Because as I mentioned, we are using the local SSD for Presto cluster, and the Presto cluster cannot be too big, only maybe 200 or 400 workers. And for each workers, there's only maybe 1 terabyte. For some companies, they only give us 500 gigabytes to cache on each worker, which means if you have because for such a big cluster, I mean for 200 or 400 Presto cluster, typically they will access 50 terabytes data per day, but actually they only have maybe 20 or 50 terabytes local cache disk. So you can see it's far way less than maybe 100% of your data. By doing some early research with Uber, I forgot to mention all about talk about the consistent hashing, about the insufficient rate, is the work, collaborative work with Uber and Alluxio. So Uber doing some tracing, they found if we can use 1% of the caching space, we can get more than 60% of cache hit rate. But the sad part is we are far way less than 1%. And if we just use this kind of cache space for Presto, we are seeing really low cache hit rate, and also we are seeing heavy eviction because always the new data comes in, it will make the existing cache entries got evicted. We are flushing the SSD all the time, and also it's a burden to the duration of your SSD, because the SSD, they have some hard limitation. You cannot always write new data to the SSDs. So they are thinking about, and also we found some table is not really cache friendly. It's not, we cannot, the table is not cache friendly. It's something like just some query on that table is not cache friendly. It will always read some old data. It's rarely use the data, and again. So it will also make some bad data into the cache. So we are thinking probably we can, based on our experience, we only cache a certain number of the most valuable and hard table into the cache rather than cache the entire data. So the Uber team contributed something called a cache filter. So for other companies, you can implement your own cache filter based on your domain knowledge to design the filters. And also we have some other approach, but it's not production ready. It's more like research things. We are making something we call shadow cache. It's more like a Bloom filter. We call cuckoo filter actually. It's my colleague Bin's research. It was more like a counter. It will counting the the usage of each partition. It just use very limited memory space. They can record a lot of things. And then based on the knowledge from the shadow cache, we can make some dry run. And then based on the shadow cache, we can have more idea about which tables or which partitions should be cached. And also, because it's real time, we can make some dynamic or adaptive cache filter based on the shadow cache. Okay, the other solution is, okay, the local disk is limited, but we can use the remote disk, the remote Alluxio cluster, because I'm working for Alluxio. So Alluxio provides something like a distributed caching storage or file system, just like the third column is the system cache. It's just the remote cluster. It's a separate Alluxio cluster. You can deploy 1,000 nodes there, and each node may have 4 terabytes. I heard some of our customers, they are using 512 terabytes HDDs somehow, or SSDs for each Alluxio node. So you can have a super huge second level cache, and you can still use local cache as your first level cache. And then if it's not hit the local cache, you can still hit the secondary cache. If it's not cached in the secondary cache, you can load it from your cloud. We see a lot of benefits when you run the query cross region, cross cloud, which means you are reading data from the remote, because the egress cost is super expensive. For some big query, for maybe take you 100 or 1,000 US dollars. So by doing so, you can cache some data in the Alluxio cluster. But today I'm just sharing the work in the community. I'm not selling Alluxio, so it's just one solution. Okay, so here's some results from Uber. They are seeing the cache hit rate from the 65% to more than 90% just by they only cache some particular tables based on their traffic patterns, because this table is the most hot tables, and also this table is not changed too frequently, just because, as I mentioned, we are adding a last modified time into the cache key. If some table keep updated, which means you always do the cache miss, right? Because you always generate a new key. And also, I strongly recommend, before we are applying any cache filter, we need to have some table level metrics. But unfortunately, this kind of code is still not merged to the master. If you want, so this is a feature, you can ping me, and maybe we can work together to trying to collect some table level metrics. Based on the table level metrics, you can have more insights about which table is more valuable to cache. Okay, I talk a lot about the caching and the Presto and Iceberg and S3. So here is some general tuning tips, because it's not always true to do some optimization, some best practice. We need to know which one is the real bottleneck to your system. I think the first one is the efficient cache space. How do we know we are getting the efficient cache space? We are just seeing the high eviction rate mostly. That means we need more cache space. But it's also not always true, because sometimes just because your query, your table, your data is not very cache friendly, it's just always flushing your cache. So you may see that by adding maybe to double your cache space, but the cache hit rate is still low. So in this case, we should filter out this table. Also, we are seeing some hot workers. It can be Presto workers, can be a Alluxio worker, because we are doing something based on hashing. So if some tables always scan the same files, especially for some small tables, you may see it always assigned to the same workers, so that worker may become too hot. So that's why we invite the soft affinity. So if the worker is too hot, it will go to some other workers. But it's still a trouble, right? So we have to watch. If it's always some hot worker, we can try to hack a little bit on our schedulers to make the soft affinity more flexible for some particular file. And also, if we are talking about the secondary cache, we're talking about HDF or something, we are seeing the bottleneck may become from the Alluxio master or from the HDFS name node, because as I mentioned, the Presto won't store any metadata. So for each query, it will try to list the files, get the files data from the name node of Alluxio masters. It might become a bottleneck. But for Alluxio, we are doing some new architecture design. We call Dora. It's already released. It's something like a masterless solution, so which means something like HDFS, but we don't have a name node. And also, we might also seeing some insufficient memories on Presto. We may see OOM, we may see high GC times. So in this case, I might recommend to use your SSD as the cache storage, because some companies, they are using their memory to cache the data. It's not necessary because the memory is too fast for Presto. If you're using memory as the I/O, you may see it didn't speed your query much. That's because, as I mentioned, the Parquet is a structured data. If you want to parsing the Parquet file, it's really a CPU-intensive job. So, which means maybe your I/O is fast enough, but on Presto side, based on the limitation of your CPUs, it can only consume maybe a small amount of data on your I/O from your I/O cycles. So it's not necessary. So we recommend to use some SSDs. NVMe is better, but even some companies are trying to some SATA SSD. It's also okay. It's good enough for Presto. So then, which means we can have more memory for Presto to use. We can see if more memory is there. It can highly reduce the OOM issues and the DC times. And also, because we are storing some data in the local SSDs, we are seeing some bugs there. It's not bugs on our side; it's bugs on the SSDs. For some particular sections, they may see some honing disk issues. You may see some timeout errors. We didn't got a good solution, but that's at least the issue here. We have some timeout on the Alluxio side, but if you're seeing this, probably you'll see some slow queries. And also, because some of the queries, they have some clumsy query plan, just because the Presto, especially Trino, they enable the CBO, the cost-based optimization by default. They will try to collect some stats from the underlayer storage, but if you're using cache, you may mess up. So this will have some unexpected behavior to the CBO. You may see some plan become really crazy. You may see some really odd plan there, so you may see some query become really slow. But this is not a common issue. Just for some particular issue, we are seeing strange queries. Okay, I think that's probably about everything about my talk today. And here is actually it's a survey from my company Alluxio. It's from Alluxio community. You can scan its code and do the survey. So this is just five question survey, and there's a chance to win the Amazon gift card. Yep. So it's the time for QA. Thank you. Yeah. Any questions? No question? Good. No, you have to use the microphone because it's recorded. Yes. Are you okay?
Just a quick question. So have you been able to compare between Presto and Snowflake in regard to Iceberg and Alluxio stack? Like using Snowflake as a SQL query engine instead of Presto?
It's hard to say. The compare you mean about the performance or
yes.
something? I don't have a formal benchmark because we cannot do apple-to-apple comparison because everything should be different. And because the Presto is more like a much inexpensive solutions. We don't maintain the data. Actually, the storage for Presto, for Spark, they can be shared. So it's really, you're talking about the performance. I think it's not fair to Presto because Presto is always trying to load the data from the remote, but right, it's not because Presto won't keep any data. But for the Snowflake, it's always do the data injection. Right? It keeps data on their side. You pay the money for their storage, but for Presto, there's no cost for the storage. Because we do compare something like a Presto with BigQuery. We can see some of the queries maybe on par, but a lot of queries, we can see definitely the BigQuery is faster because they are building their own data on their storage. They are more, the computer engine is more close to their storage. Okay, so let's go to my story because we are doing some local cache, but there's still some limitation. As I mentioned, the local SSD of the Presto is very limited. So mostly for some query, for the query in Facebook, they are seeing 10 times speed up they call it RaptorX project. You can Google it. They post a blog I think 2 years ago. But for some companies, they only seeing by using local cache, they're using 10 or 20% of the improvement of the performance. So that's really hard to say. We cannot always do the apple-to-apple comparison. For each company, they may have their own use case. They may have their own bottleneck. But the only thing I can share is by using the local cache, it can somehow speed up your query, and it can also save your cost about your storage. Because Uber is using this local cache, after using the local cache, they found the workload of their HDFS clusters got 8% or 10% reduced. Because they don't need to load data from remote. They just always hit the data in the local ones. It can speed up the query, they make your latency more stable, but also save your cost. Because for the Uber, they just maintain their own HDFS. But if you are storing data on your S3, if you're running some Presto on another cloud, it's very common now because many companies, they want to build their compute in one cloud, but they're storing on the other cloud. You're always fetching the data from the remote. So by having some cache, whatever cache they have, you can save some cost.
Thank you.
We're talking about the cost, sometimes talking about the performance, but for the some cloud native solution like BigQuery, like Snowflake, I have to say they're extremely good. They are doing everything together. They're more like a big elephant in the room. They have everything. If you really want to pay the money, you do the data injection there, you can get really good service. But here, I'm more talking about the open source solution. You have to build up your system from scratch, everything by yourself. And then at the very beginning, you may say, okay, it's not so stable because we have a lot of dependency issues. The one service will connect to the other. If any of the dependency offline or something, the query failed. But for the snowflakes, if you inject data there, it's always true, it's always correct, it's always running there. It's cloud.
Got it. Thank you.
Any other question?
Any other questions?
Okay, we are good.
Thank you very much. Appreciate it.
Thank you.